Hi there, this is Professor Jim Caffey again, coming to you from Springfield, Missouri, and we are going to talk about Chapter 18 on Stars, a Celestial Census. So this will continue our examination of stars. We see a variety of stars in space. Some are blue, some are red, some are big, small, hot, cool, massive, not massive. They come in all sizes and colors and temperatures. We do have a couple of stars that are the closest. They are about 4¼ light years away. So when we take an image of them, we see them back in time 4¼ years. It takes that long for that light to reach us. And they are the closest minus the sun, which is 8 light minutes away. So when you see the sun, that's how it looked 8 minutes ago, not now. One of the things that I'm an expert in is binary stars. So this is a visual binary, a cool L-dwarf binary, and we can see how it rotates in space with each other over time. It takes a long time. In a binary star system, you can have two stars of really any mass to work with. High mass stars are going to kill off the low mass stars in a binary system. They evolve and they get absorbed into the bigger star. We can see the motions of stars in a binary system. We can look at the spectrum. And in a spectrum, the dark absorption lines will shift back and forth as you see the two stars in the pattern. You only see that spectrum in pictures 1 and 3 where that motion is towards us or away from us. Remember, we recently talked about red shifts going away and blue shifts coming towards you. If the stars are sideways, a tangential motion, we can't tell if they are moving away or near us. And we call these measurements radial velocities. Now, in studying an eclipsing binary system, this is a special kind of bevel star or a binary star. In an eclipsing binary system, the one thing I'm the most expert at in my research is you have to take images on a camera, pictures, and measure light brightnesses as they go in front of each other, just like a solar or lunar eclipse. One light is going to be blocked by the other, and we can tell that by seeing less light at the telescope. You combine that with the radial velocities in the spectroscope, and we get a full picture. I like this feature where I can zoom into me and talk to you for a minute. I like that. Makes me feel like I'm in a classroom. We have some failed stars, brown dwarfs. We talked about these last time in chapter 17. A brown dwarf is a star who could not kick on thermonuclear fusion because its mass is not great enough. It needs to be about 8% the mass of the sun. And the sun is actually a yellow dwarf star. So it doesn't take much star matter to make a star turn on and shine. We have a mass luminosity relationship with some stars. Cepheids that pulsate, yellow big stars that pulsate, and white dwarfs and other stars. Now here is what I did for 20 years in my research with NASA in Missouri at Missouri State University. This is where I said you can take an image of the two stars and collect all the light. So we can do that. And in that we get this neat light curve. This is what we call the change in brightness over time in an eclipsing binary system. We also use light curves in other areas of astronomy, but you can't see the two stars together in a telescope separate. They are too close to resolve as two. So we use this to get the spectra, and we get the photometry, the light measurements. Unfortunately, my telescope at Missouri State University did not have a spectrograph, so we could not get radio velocity measurements. So I didn't get a full picture of what I wanted to. A perfect eclipse in an eclipsing binary system, well, it can look like this. Depends on the size of the star, how fast they are moving. This one seems to be at a moderate clip. You see a smaller star. It is completely behind the other star for a period of time. We call that a total eclipse. And then it starts coming out of eclipse and exits. And the light goes back to normal. But these two men were giants in astronomy. Hertzsprung and Henry Norris Russell independently discovered the relationship between luminosity and surface temperature of stars, or color, brightness, magnitude. This is summarized in the most important diagram that I can identify in astronomy, and that is the H.R. Henry Norris Russell Hertzsprung Russell diagram. So for a few stars, stars that are normal, they are burning hydrogen, they are not doing anything weird, they fall on a curve called the main sequence. These are all normal stars. Some are cool, some are big, some are hot, but these are stars in their adult lives. We talk about stars as they are living like in adult lives. So stars are protostars, babies. They are born, they kick on in fusion, they shine for billions of years or however long, depends on their mass. The sun will burn for 10 billion years and has been for 5. If we look at many stars, we see that about 80-90% of all stars do fall on that main sequence. And this chart looks different many ways. You can graph this many ways, but you get the same result. So this is a very powerful graph to get temperature measurements, brightness measurements, spectral class, surface temperature. How big is it? Is it a supergiant? Is it a red giant? Is it a tiny red dwarf star? That's what I'm an expert in, is red dwarf eclipsing binaries. Is it a dead star? Is it a white dwarf? So we can look at the sun, a dwarf yellow star, and VY Canis Majoris, a supergiant. And when I say this is a supergiant, it's really obnoxious. The sun is just this tiny, you can't even see it, this dot. That's the sun put next to VY Canis Majoris. It is I think it's the biggest star that we know of. We have seen a dwarf companion star, a white dwarf, around a very famous bright star called Sirius, the dog star. That's going to complete the lecture for Chapter 18 on the stars. Thank you for joining me, and I hope you will continue to join my lectures.